So previously we had discussed the concept of matrices and transposing them from some matrix A to A transpose, and we'll kind of briefly review that in a moment. But another primary and major concept that we did talk about is the concept that if we have a given matrix, some matrix right here, and we have a series of rows and columns, we can essentially express this matrix and we can group them together such that it is essentially composed of a series of bras or cats, meaning that it's, for instance, in this case, we can name a number of bras A1, A2, right? And it's a matrix composed of these vectors. And what it makes that quite interesting, quite curious in itself, is that in such a way we are having and we're dealing with what arguably can be considered, a single column or single row, and then it's much easier to conceptualize and consider a number of computations relating to them. Alright, so all things aside, let's clear the board and let's consider the following instance. So let's say we have some matrix A, right, and let's say A is some one single row matrix, and we'll name the elements B. So it's composed of a number of kets, so B1, right, B2, and so on and so forth until we reach Bn. Alright, now if we transpose the matrix A, and remember transposing is essentially where we take the columns and make them into rows, and the rows into columns, and then we can say A transposed, right, is going to be in this case a single column composed of the bras B1, B2, so on and so forth until we reach Bn. And just keep in mind n is just the index in this case. So going on from there, let's try to find the product of A transposed and A. Now, what's curious here is that when we take and transposed and multiply by A, we'll end up with a n by n. So remember, n is the index for the size of this given. So this is 1, right, and this is size n. This is 1 and n. We're going to end up with an n by n sized matrix. And so let's consider this multiplication. Let's compute what that means. Alright, so if we take A transpose and multiply it by A written out, that is simply equal to some B1, right, B2, as we established earlier. And this is just merely writing it out so we can kind of touch on all of the basic concepts previously, right? Bn multiplied by B1, B2, and so on and so forth until we reach Bn. Now, if we go on and just follow the rules of general multiplication, right, and we just multiply them together, what we end up having is something along the following lines. This should be equal to a matrix, again, has dimensions n by n, composed of B1 and B1, so B1 multiplied by B1, and then B1, right, and then going to B2, and so on and so forth until we reach B1 multiplied by Bn, which is essentially your last element in this given kind of row here. And if we continue this pattern, then we go to B2 for your second row, right? So B2 multiplied by B1, so B2, B1, right, and then B2, B2, so on and so forth until we reach B2, Bn. And if we continue on in this general pattern, what we end up encountering is something along the lines of Bn by B1, right? And at this end down here we have Bn by Bn. Right, if we continue down in this general vertical direction, we have Bn and B2, right? Alright, so taking a look at this general kind of matrix that we have here, there are a couple of quite curious essentially relationships and items that we can notice and take note of. So first things first, of course, you might kind of be drawn to the idea that this entire diagonal that we have right here across the matrix, right, this diagonal that we have consists of these vectors b1 multiplied by its transposed version of itself. So if you remember and if you recall from orthonormal and orthogonality, fundamentally, there's a number of properties that can be determined as a result of given relationships between these vectors and these kets, so on and so forth. So orthogonality. And keep in mind, from a geometric perspective, this is kind of similar to saying, consider, for instance, having a given vector on a graph, such that these two vectors are at right angles to each other, then they're mutually orthogonal. And if we do want to figure out if these kets are essentially units, then we can take, in this case, for instance, b1 multiplied by b1, right? And that should be equal to 1. b1 by b1 should be equal to 1. Right? And going on from there, there's an additional kind of consideration that we can make. So in order to show that a certain set of these kets are, for instance, mutually or orthonormal to one another, that means mutually orthogonal to one another, making up an orthonormal basis. Do not get that mixed up. There's a number of things that we can consider, most importantly being that each one of these elements beyond the diagonal, so this is diagonal again, right, where these n match up to each other, where any of these elements not on the diagonal are equal to 0. So b1, for instance, times b2 is equal to 0 if and only if you have an orthonormal basis on your hands. Now, from a more general perspective, from a more formally defined perspective, in order to have some given set of these kets, and in order to show that they are mutually orthogonal to one another, right? In order to show, there's no comma there, in order to show that some set, right, a set of these vectors, and we're just considering of vectors a little bit right now because this matrix is composed of a series of vectors. A set of vectors are mutually, a set of vectors compose an orthonormal basis. Right, we need essentially the primary condition of them being mutually orthonormal to one another. And again, as we showed previously, this means that we are considering unit vectors because, once again, for any ket multiplied by itself, right? So what this means is that for any ket bi multiplied by the broad bi, and I kind of got that backwards right there, this should be equal to 1, meaning that it's a unit vector. So for instance, if your vector is 0, 1, and you multiply it by itself, ideally this should sum to 1. Right? Alright, and the second condition here is that for some bi multiplied by bj, where I does not equal j, ideally this should be equal to 0 here, just because they are, again, quote-unquote perpendicular to each other, and as we established previously, it should be equal to 0. And so from this, actually, we can use this kind of method, taking A transpose multiplied by A, in order to determine whether or not this set is essentially an orthonormal basis. It makes up an orthonormal bases. Now, if we want to kind of go through the steps of figuring it out, of course, it can be a little bit tedious to have to go through and say, hey, let me check this one, then this one, and then this one, and this one, and kind of go through all the steps and check every single multiplication and computation on there. So actually, if you note, there is something interesting here that we can kind of keep in mind. Here, ideally, primarily is just that we just have to check everything either above or below the diagonal, and keep in mind this here's the diagonal here, just because, and let's see if I can find enough space for this. You only need to check one side of the diagonal, which means either this side, or alternatively just everything on this side, because if we have b1 by b2, and let me use a different color here, right, we have b1 by b2. Actually, if it is mutually orthogonal, that should be equal to b2 by b1, and that is the general concept in it. And so, essentially, when these two bracket kind of products are equal, then we don't just basically need to calculate both of them. That will save us quite a bit of time. Alright, so let's go on and consider a couple of things and tie it back to what we've discussed earlier. So as we know, based on what we just said, let's say we've shown that for some set, right, B1, some cats, B2, to Bn, right, we've just used this method of A transpose multiplied by A to show that this set here, again, A is just some matrix composed of the elements within this particular set. We've just used this method to show that is an orthonormal basis. So if we have some vector v here, and we'll use a different color, some vector v, and we want to show it as a linear combination of these bases vectors, we then know, based on this information that we have here, precisely how to do this. As you may recall, if you want to express anything as a linear combination of the bases vectors, the general kind of concept is to be able to take each individual kind of pairing in this case and essentially express it as the sum of some value multiplied by it. So based on what our previous calculations were, if you have some vector b1 and b2, right, and this is just kind of separate from what we have here, right, and you want to express some vector v in terms of just b1 and b2 where they're mutually orthogonal to one another. The general kind of concept in here with a two-dimensional version of it, it would be just to take some vector v, right, some vector v, and multiply it by the bracket product. Right, let me make sure I have the notation correct. Right, and those kind of relationships that we had established earlier and previously. And so going on from there, with this kind of general sort of two-dimensional kind of concept in mind, let's apply it to just a little bit more generic version with a set containing these multiple kind of cats that we have here. And so we can express this vector just following the same kind of relationship right here, right? Instead of two-dimensional, we have n-dimensional in this case. Then we can take it and express it as just b1, right, the product b1 multiplied by the vector v, b1, the cat vector b2, v, b2, and so on and so forth until we reach bn, v, and bn. And so that's how you can solve for fundamentally the linear combination and express any sort of vector as a linear combination of these bases vectors. Apologize, I realize now this is not entirely multi-dimensional quite yet. We're just merely looking at a orthonormal bases and attempting to express it as a linear combination of these bases vectors in that sense. So it's not entirely n-dimensional. But either way, just to briefly recap, today we went over the concept of just multiplying A transposed by A and figuring out that if we can end up and analyze essentially this kind of the resulting matrix that we are looking at, then we can determine whether or not a given set composed of B1 to be n cats is essentially equal to a orthonormal basis. And based on that orthonormal basis, we are able to express some vector as the sum of these orthonormal bases in the following relationship here. This is the generalized version of that relationship, and so we can kind of go forward with that in mind. Alright, so that's it for today. If you have any questions, always just feel free to check out the Community Quantum website. And as always, stay curious and keep on learning.